This video is entitled The Design of Phase 2 Studies, Technical Details. Today's presentation will focus on Phase 2 study design, but the general principles apply equally to other studies, for example Phase 1 and Phase 3 studies. The key message is that the design is critical to the usefulness of the subsequent modelling and simulation results. And the goal here is to talk about using tools to prospectively assess the quality of the modelling and simulation results. And the recommendation is that we should do this always. Retrospectively, we can repeat a poor analysis, but we cannot fix a flawed design. So if we're recording the observations at a poor time, or if we not have enough subjects, then we can't fix that afterwards. Within this presentation, often I'll present numbers to many decimal points. It's not because they're that accurate, but just so that if you wish to replicate these numbers, you can see if you can generate exactly the same numbers. In principle, the Phase 2 design problem is about selecting the doses and the weighting for each of those doses. The idea here is that we would select dose 1, 2 through to dose n. And we can think of doses either being on an exact scale, so a selection of doses, or dose on a continuous scale. Similarly with the weights, we can think about the weighting for each of the selected doses. So for example, down here we have an example where we have placebo, 5 mg, 15 mg and 100 mg. The weighting is 25% of the sample size at each dose. And for example, that would be maybe 100 patients at each dose level. For a longitudinal model, so where we're modelling the change of the response as a function of time, we would have perhaps an observation schedule which we would need to think about, perhaps recording information at baseline, week 2, week 4, week 6 for example. That adds an extra dimension to the design problem, but we're not going to discuss that today. So when we're thinking about the optimal design, or designing Phase 2 studies, what's the sequence of steps we need to think about? The first step we need to think about is the primary endpoint. So for example, we could be thinking about a single endpoint, so that could be the primary efficacy endpoint, or we could be thinking about multiple endpoints. So we have both the primary efficacy endpoint, perhaps other efficacy endpoints, and other safety endpoints. And we're going to be interested in the design performance across all of those endpoints. Secondly, we can think about what model we're going to be looking at. If we're using dose or exposure, so the pharmacokinetic information with exposure, or just using dose. Today I'm just going to focus on using dose with the sigmoidal Emax model. The third step is to define the metrics. So how are we going to compare designs and what we can define a good design by. So for example, we're going to be interested in the precision of the dose response curve, how accurately precisely we're estimating that dose response, and we're going to introduce the idea of efficiency. And also we can think about the precision for any model-based metric. So it doesn't have to be particularly about standard error or width of a prediction interval. It could be any metric. The metrics will need to be evaluated over the parameter space and the design space, with the design conduct in mind. So the first thing we need to think about there are what are reasonable estimates for the parameters of our model. So we can use point estimates. So for example, the Emax is 1, or the E0 is 0, or the ED50 is 10. And we can think about an optimal design, and they're typically called locally optimal designs. Or we can think about those parameters belonging to some form of joint distribution, and we can talk about globally optimal designs and scenario-based results, and we'll go into that. What methods are we going to use to evaluate designs and then optimize designs? We have two choices here. We can talk about optimal design theory, so a theoretical approach based on the expected Fisher information matrix, or we can talk about the clinical trial simulation. We just simulate up the studies and re-estimate them. And finally, how will the study be run? Typically today I'm going to be focusing on fixed designs, but I'm going to introduce adaptive designs as well. If you're fairly new to designing studies, some of this presentation may seem complex. What I wanted to say with this slide is that you can start with a very simple yet informative initial project. So for example, here we have one endpoint, it's an efficacy endpoint, and we have perhaps an Emax of around 5, an ED50 of around 10, and a Hill coefficient of 2. And perhaps a metric we're interested in is the dose required to get an effect of 3. So what we could do is simulate a proposed phase 2 study design. We could do that 1,000 times, estimate the dose response curve, and here we have, for example, 1,000 estimated dose response curves. And what we could do is we could compare the predicted dose required to give it a 3-unit change. So here from around about 8 up to about perhaps 20, which is what we're seeing here in this histogram over here. We have the 90% prediction interval from 8 up to 20, and we can compare that to the true value. If we know that the Emax is 5 and the ED50 is 10, the dose required should be at 12.25. And we can see how close we are. And then we can talk about whether we think our design is adequate enough or not. Step 1 is going to be defining the endpoints. Clearly, we cannot hope to consider every endpoint. It seems reasonable to focus on at least one efficacy endpoint. We can compare that with a power calculation, where we typically focus on the performance of a particular endpoint, and perhaps one safety endpoint, to have some sense of how your design is going to do for a safety endpoint. A potential final design can be evaluated but not optimized across multiple secondary endpoints. So perhaps we're not going to optimize the design based on secondary endpoints, but we can still look at how the study is likely to perform on those secondary endpoints. We have some sense of how well it's doing on those other endpoints. We would need to define a model. So here, during this presentation, I'm going to be focusing on sigmoidal Emax model, describing a dose response. And we're going to use it to demonstrate a number of key points about the design performance. So here we have the standard equation for the sigmoidal Emax model, and here we have perhaps an output from a modelling exercise using that model. Where has this come from? Well, it's come from a model where the estimated Emax, which is down here, is about 1. The ED50, which is estimated on the log scale, is around 10. The Hill coefficient is around 2. The E0 is 0. This design over here is actually the optimal design. So it would select a dose of 0, a dose of 100, a dose of 5.76, and a dose of 16.09, and these will be equally weighted. So with a total sample size equal to 1,000 times the residual variability here, this is the expected variance covariance matrix. And we can see here that the diagonal elements of the variance covariance matrix, if we take the square root of this number, this is our standard error. If we take the square root of this number, this is our standard error. Finally, we should just mention that the determinant of this variance covariance matrix is 1.28 times 10 to the minus 8. If you actually cut and paste these numbers, I think you get a determinant of 1.26. That's just because of rounding. The residual variability up here, if this was 1, we would need a total sample size of 1,000. So a residual variability of about the same size as the Emax here. So that would be 250 patients at each dose. And if this was 0.2, it would be a total of 200 patients. So about 50 patients at each dose level. And if we use this variance covariance matrix to calculate a 90% prediction interval, it would look something like this. Just to mention, if you try to replicate the optimal design here, it's worth noting that the maximum dose here has been set at 100 milligrams. That's about 10 times the ED50. If you allow this to go higher, it will change these numbers slightly, but just to bear that in mind. Step 3, when we're thinking of comparing designs, efficiency is a very clear way to convey results. So in this example, we have a design 1, where we have placebo and 4 doses that are quite closely spaced, versus design 2, where we have placebo and 4 more widely spaced doses. And perhaps if the output from this design based on n equals 1,000 yielded this type of metric and result, if we obtained the same result down here as up here, but with this design it was with 500 patients. The efficiency of design 1 to design 2 is at 50%. We would need only 50% as many patients here as here. When there are multiple endpoints and metrics, the overall performance can be determined using efficiency. So in the previous example, we compared design 1 versus design 2, and we said that the efficiency was 50% on that metric. Perhaps if we had a second metric based on that endpoint, the efficiency may only be 25%. Similarly for endpoint 2, we have metric 1 and metric 2, and we see here that design 1 is actually doing better versus design 2. So we can think about, well, how would we calculate an overall performance here? Because if we're trying to rank the designs across both the endpoints and the metrics, we need to come up with perhaps a single number. And we can think of an equal weighting here where all 4 of these are considered equally important. And we come up with an overall performance here of 84%. And it's essentially just a geometric mean. Alternatively, we could give an unequal weighting to the different endpoints and metrics. So here, endpoint 1 is considered a little bit more important than endpoint 2. And again, we can calculate the overall efficiency here. So design 2 would need 71 patients for every 100 patients we would need with design 1. But what metrics are we interested in comparing and optimizing? Well, we're going to start trying to work backwards. I'm going to give an example where we work forwards and show how we would normally then try to work backwards. So imagine we had observed a result like this. Perhaps we have an Emax estimated at 1, the ED50 is estimated at 10, the Hill coefficient is estimated down at 2, and the E0 is at 0. And we have these standard errors and this variance covariance matrix. What we would normally do then is to go from maximum likelihood estimation, we would move towards a posterior distribution, so the probability density function for the parameters given the data, and we often apply the multivariate normal approximation. And what we're arguing here is that the posterior distribution of the parameters given the data is essentially multivariate normal with these means and with a variance covariance matrix like this. And if we do that, we can look at the determinant here of this matrix, so how big the variances are. It's a measure of the size of the variance covariance matrix. And we can actually obtain a result like this as well by taking samples from that multivariate normal distribution to generate 1,000 dose response curves and then summarize them with the 5th and 95th percentiles at each dose. So if you've heard of the optimality, it's about minimizing the size of the determinant of the variance covariance matrix. So if you take the determinant of this matrix, it should be 1.28 times 10 to the minus 8. And we want small diagonals here because we want small variances, we want small standard errors of our parameters. If we're working with the Fisher information matrix, we want to maximize the determinant because it's the inverse of the variance covariance matrix. V-optimality is about the size of the prediction variance. So it's the size here, or perhaps the size here, or the size here of this prediction variance. And this is very important. I would argue that V-optimality is more important than D-optimality because the size of this variance covariance matrix is not so important relative to the size of these prediction intervals that we generate. And we can think about, perhaps we could look at the size of the prediction interval at all these stages here. So here we see it's about 0.29. From down here up to up here, it's about 0.32. And here up to here, it's about 0.27. And perhaps we could focus on the size of all of these, or perhaps just some of them, ones in perhaps the more important range. So around ED50, 2 ED50, and 4 ED50. And we could define where we want to be precise. Whilst D-optimality is easier to work with, equal D-optimal designs can yield markedly different prediction intervals. So what I've done here is just generate 2 matrices, variance covariance matrices with the same determinant. So they're considered to have the same size as that D-optimal design. I've just made them diagonal now. So if you multiply each of these numbers, you'll get this number here, except for any rounding issues. Here, to get that same determinant, I've actually improved the precision on the ED50, whereas down here I've improved the precision on the Hill coefficient. So these are generating the same size determinant, the same size of the variance covariance matrix as that d-optimal design. But we see that when we use this variance covariance matrix to generate the dose response with the uncertainty around it, we see that the shape looks very different here. Here obviously it's quite tight around the ED50 because we have this high precision, but it's less precise over here, whereas over here we have a different looking curve. So just to mention here that when we're working with d-optimality, it's very nice, but actually it's not really what we're interested in. I think v-optimality is much more important because it's talking about the size of the prediction variances here. As an example, we'll just give a quick introduction to v-optimality. It's a little bit harder to work with, but I can just show you how it can affect the design. So for this model that we were looking at before, we have the d-optimal design. So we had doses of 0, 5.76, 16.09 and 100. And what we can do is we can look at the size at each of these dose levels of the prediction interval, the 90% prediction interval width. So this is from this number here up to this number here, which is about 0.08. Here we see it's 0.07. These numbers were generated on 10,000 replicates. The graph was just done on 1,000. So there's some slight differences between this column here and what you see on the graph. So here we see it's 0.16, it's 0.15, 0.27, 0.27, 0.32, 0.31. So these numbers are about right. When we look at the v-optimal design, so this has been searched for to try to find a design that makes these intervals smaller. What it tended to do was it put more weight on placebo. We had 6, 16 and 100, so we just looked at some discrete values for the different doses here, and we see that it came up with this type of weighting. And if we look at that v-optimal design for the same sample size, we can calculate the width of the 90% prediction interval. And what we're interested in is comparing these numbers with these numbers. And in the middle here, we have a D star, which is just a d-optimal design, but with 7% more subjects. And if we look at the average width of that 90% prediction interval for the d-optimal design, the v-optimal design is doing better. And if we take the d-optimal design and increase it by about 7%, we get something similar. Another way to present that is with efficiency. We can look at the efficiency across the dose range. So we see that the d-optimal design, the width of those intervals here are generally larger, with the exception of the first point here, are generally larger than they are for the v-optimal design. So the v-optimal design is doing better. It's getting a smaller 90% prediction interval. And we see this with the blue line. And the average of these blue lines is about 7% worse. The star design, the optimal design with 7% more subjects. And we can look at the efficiency across the dose range, and on average this is performing about the same as the v-optimal design. So as we would expect, the v-optimal design is doing better on the width of those prediction intervals because it's been optimized for that. The metrics can also go beyond precision. For example, the predicted probability of success for different sample sizes in phase 3. So in the introductory lecture, we showed this graph, which is the predicted treatment effect for a given dose. So for example, at 8 milligrams. And what we can do is we can take this distribution of the predicted treatment effect to generate the probability of success in phase 3. So if we obtain this in phase 2, we can turn that into a probability of success for different doses. So here is the 8 for different sample sizes. For here is 300, for 500 and for 1,000 per arm. And what we may see is that perhaps here we need about 300 patients per arm in phase 3 for 8 milligram to be a success. But what would happen if instead of obtaining this distribution here, we'd obtained a much flatter distribution? So the phase 2 design was smaller, so we've saved money in phase 2. But what that's led to is that the predictions for this dose level are now much wider. So this would be much flatter because we're less confident about the exact size of the treatment effect for this dose. What that would mean then is that when we take that distribution and try to talk about the size of the phase 3 study, we're going to end up needing a much larger phase 3 study because we're much less certain about the size of the treatment effect. So here, for example, in this illustration, perhaps we would need 500 patients per arm because we ran the phase 2 study quite small. So you can think of a better metric would be the combined size of the phase 2 study and the phase 3 studies. If we run very small phase 2 studies, we may end up needing very large phase 3 studies, whereas perhaps if we run larger phase 2 studies, the phase 3 studies will be smaller because we'll be more confident about the size of the treatment effects. So steps 1 to 3, a recap of just where we are so far. We've defined the endpoints, we've defined the model, and we've defined the metrics, and we understand how, using efficiency, we can compare those metrics of one design to another. There's 2 main steps to consider next: the values of the model parameters and methods for comparing the designs. That's what we're going to talk about now. So when we're trying to work across the parameter space, and what do I mean by parameter space? It's just the different values that the parameters can take. Our starting point is this paradox. To design the experiment optimally, we need to know the true values of the nonlinear model parameters. So in a nonlinear model, the optimal design depends on the parameters. But the reason we're running the study is because we're trying to estimate those parameters. So we're trying to estimate the Emax, we're trying to estimate the ED50 because we don't know them. Well, if we knew them, we would know the optimal design. The way that we approach this is that we think about the performance across different potential values for those parameters. The first way is with global optimization, using a joint distribution of those parameters. So we don't just say that the Emax is 1, but we say, well, we think the Emax is 1 and it follows this distribution. Or the ED50 is 10 and it follows this distribution. Perhaps it's a low or perhaps it's high, and we look at the performance across that distribution. And the other alternative is to look at scenarios. So global optimization requires integration over the parameter space. So if we're trying to work out a globally optimal design, what we're going to do here is that we're going to work out what is the best design given the uncertainty on our model parameters. So for example, here for de-optimality, we would integrate over the log of the determinant. It's called the API method. So we're integrating across our parameters, theta, our model parameters, of the log of the determinant times by the probability of those parameters. So here, for example, for a sigmoidal Emax model, the optimal design consists of the lowest dose, 0, maximum dose, and the middle 2 doses depend on the ED50 and the Hill coefficient. And perhaps from an earlier proof of concept study, we've obtained something like this. We've got an estimate that says the ED50 is around 10 and the Hill coefficient is around 2. But we have uncertainty on those estimates. And perhaps they follow this joint distribution here, as shown in the red or the green or the blue with the different contours. So this is a bivariate distribution. And what we can do is we can look at the performance not just at a single point here of the design, but we integrate across this entire joint parameter space. And that's what this integration sign is doing here. What's good about globally optimal designs? Well, they yield the best design. Given our current state of knowledge, it comes up with a design which is going to do best. It's going to weight this point more heavily than this point, and these points and these points, and that's what we would expect it to do. A criticism is that we have no idea how bad things might be. So we may come up with the optimal design, but what is the performance likely to be here, or perhaps over here? It would be important for us to perhaps understand that rather than just knowing that it's the best design. Perhaps the best design is still doing quite poorly if we've poorly defined our parameters. And the second thing to maybe comment on is it can be a lot of number crunching, especially if you're doing clinical trial simulation and you're trying to do this over the joint parameter space. If you're doing just something like this, the determinant of the Fisher information matrix, it perhaps is going quick and we can do this integration perhaps over 1,000 samples very, very quickly. Another alternative, rather than doing the integration over the joint parameter space, is just to pick points on the parameter space. So here we can think about scenario 1, where we use our estimated parameters from perhaps the proof of concept study. And here we maybe look at how it would do under scenario 2 or scenario 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we get 13 scenarios where we look at the performance of one design versus another. And then the idea there is that we actually generate good understanding of where our design is going to be doing well and when it's going to be doing poorly. A problem both for the scenario-based method and the global optimal design method, in fact, is the difficulty in multiple dimensions. So for the sigmoidal Emax model here, we're just working in 2 dimensions with the Hill coefficient and the ED50. But if we had multiple dimensions, perhaps it would be hard to select scenarios that nicely map across all those different parameters. How to compare designs and find optimal designs? Well, there's essentially 2 paths that we can go down. One is optimal design theory, so that's working with the expected Fisher information matrix. And the other is clinical trial simulation. Clinical trial simulation is simply we simulate the study and we re-estimate it, and we look at the values of the estimated parameters versus the true values. Quick comparison between these 2 different methods. One of the big advantages of clinical trial simulation is it incorporates the estimability of the design. Because we're simulating the study and then we're estimating it, we get a good sense for actually how it's going to likely to perform in practice. In contrast, an optimal design may be optimal, but it may actually perform terribly in practice because the residual variability is so large that for a given sample size, it actually cannot reliably estimate the parameters, even if it's an optimal design. A problem with clinical trial simulation, though, is because we're doing these estimation steps rather than perhaps here where we're just calculating the determinant of a matrix, this is going to take a lot more time. So even though we can find examples where optimal design can be slow, if we have multiple differential equations, integrating across a global parameter space that's huge, with lots of design flexibility, of course this could take a very long time. But generally, if we're actually trying to do all those same type of designs, but we're actually simulating them and then re-estimating them, it's going to take a lot longer. A third thing to mention is that the results will be dependent on sample size. So for optimal design, you get an optimal design, but it doesn't change whether you talk about n equals 100 or n equals 1000. It's still the optimal design. With clinical trial simulation, we could imagine that perhaps one design would do well for a smaller sample size, but perhaps another design would do well for a larger sample size. And then we have this difficulty in trying to have this extra dimension in terms of looking at design performance. One of the big advantages of optimal design is that it can find optimal designs. So the optimal design theory says this is the best design. And when we find this design, so like we looked at the optimal designs earlier, we know that's the absolute best we can do. A problem with clinical trial simulation is that we may simulate a range of different trial designs and one may appear best, but it doesn't mean it's optimal. It may be the best of the group of 10 or 20 or 1,000 clinical trials designs that you've compared, but it still isn't optimal. And one of the reasons why it's really useful to have an optimal design is that you know what's the absolute best you can do. So then when you look at exact designs where perhaps dose isn't 5.76 but it's going to be 6 milligrams or 15 or 16.09 and it's going to be 16 milligrams or 20 milligrams, you know what the best performance was. So you know what you're losing by looking at exact doses rather than dose on a continuous scale. Another point is that optimal design provides understanding of a good design. One of the problems with clinical trial simulation is you may find one design is doing well versus another design, but you don't actually have a good sense for why it's performing well. With optimal design, you often have a very good sense for why it's performing well. Is it putting more patients on placebo? Why is it doing that? You get a good sense for what makes a good design. So if you try to come up with new designs that are doing well across multiple metrics, you can use the information from the optimal design quite clearly. Difficulty with using optimal design is it requires knowledge of optimal design theory. So you need to be comfortable working with the expected Fisher information matrix. If you haven't been trained on that, it can be a little bit difficult. In contrast, clinical trial simulation is extremely straightforward. We just simulate the design, we estimate it, we compare the estimated results to the true results. Very straightforward. Finally, I've been focusing a lot on fixed designs here. Anyone who knows me knows that I'm a big advocate of adaptive designs. I think the first thing to mention is when we talk about the universe of adaptive designs, adaptive randomization is what I'm specifically often talking about. And what that means is, it means as we go through the study, we change the probability of being randomized to different doses such that we're obtaining information in the best part of the curve. So if we happen to have a wide range of doses, and actually the doses that are going to be working that we're most interested in are towards the top end, then the design, the optimal design, is going to focus on selecting doses which are most informative based on the accruing information. And because we're doing that, we improve our overall performance of the study. In comparison of adaptive designs to fixed designs, generally an adaptive design would be valuable when the prior information is weak. So when we talked about globally optimal designs, if we have a very wide uncertainty on our parameters, then what that means is that we actually aren't very sure where they are, and therefore the design may perform very poorly. If we have good information about the size of our ED50 or our Emax, then we can make sure that the global optimal design is going to do well. Another reason why we might want an adaptive design is when the recruitment is over a long period relative to the endpoint. So if we have time to get data in, to look at it, to then adjust the randomization for the new patients coming in, that's going to work well. Obviously, if recruitment is happening in over a couple of months and the endpoint takes 6 months, then it's not going to be so useful. I think a third point would be when you want the best results for your money. So if you're going to recruit 1,000 patients, you would like those 1,000 patients to all be contributing information to your understanding of the dose response curve. It's disappointing if only half of them are actually in the area of the dose response where they're most informative. And finally, if you want an ethical design, again, if patients are going to enter into the study, it's nice to know that they're going to generate data that's actually going to be informative to you. You don't really want them going on to doses that are not adding anything to your understanding of the dose response. So I think as a summary, for me, when I think about adaptive designs or adaptive randomization, I think it nearly always be better. And I think that the standard phase 2, phase 3 designs should be adaptive ones, because I think when I look at those 4 bullet points, I would tick them each time. Some topics that I haven't really mentioned today: exact versus continuous design. So the idea that dose is perhaps continuous, so like in the example where the optimal design was 5.76. In reality, we may have dose levels of 5 or 10 or 20, and that would be an exact design, so we're using only those doses, whereas continuous designs allows them to be flexible. In terms of analysis, we can be thinking, are we going to be combining prior data with the new data, or are we just going to be analysing the new data alone? So for example, if there was a previous study that looked at a lot of low doses, are we going to now, with the new study, combine the doses that we're looking at now with those low doses, or are we going to analyse it separately? Clearly, if we're going to analyse it separately, we may need lower doses in the current study, whereas if we're going to combine them together, perhaps we don't need as many subjects at the lower doses because we're going to be putting them all together. When we're talking about nonlinear mixed effects models, we have the calculation of the Fisher information matrix, and that can be done approximately or it can be done exactly. I've not talked about that. Generally, if you're going to be using an approximate method, then it makes sense that you understand, well, how much am I actually using? So I think you'd have to use clinical trial simulation to have a good sense of what actually is going to happen. In terms of presenting the results, are you going to present the results from a single model or multiple models? So with multiple models, what are they going to be, and how's the design going to perform across those competing models, and how are you going to differentiate between models? And finally, with the adaptive designs, obviously the use of biomarkers or early endpoint data can be used to change the randomization based on early information rather than perhaps waiting for the final endpoint. So as a summary, I hope I've given a brief overview of the main steps needed to help design Phase 2 and Phase 3 studies such that they yield useful results. We know that we can always apply the models to the data set, but if the results from those models are so uncertain as to not be useful, then the design is really flawed. I think the most important first step is to evaluate potential designs for your key endpoints via clinical trial simulation. So if you know where you are, then you can try to improve the design to see if you can do better. The designs do not need to be optimal, however they must be good enough. So I think the idea of always searching for optimal designs from a practical perspective isn't so important. I think what's important is that you know the characteristics of your design, your Phase 2 study design, such that it's going to be good enough in practice. And in case it wasn't clear, designing studies properly is very important. If you are interested, here are some publications. The first publication focuses on the use of adaptive design and shows how essentially it reduces the risk because it learns about the dose response as you're going along, and therefore by learning it randomizes new patients to the best doses, and of course therefore it outperforms a fixed design. The second paper is looking at exposure response rather than dose response because the designs are different if you're planning an exposure response rather than a dose response. And the third paper here is looking at optimal Phase 2 design for a nonlinear mixed effects dose response model for count data. So here it's working with an expected Fisher information matrix, which is difficult to calculate, but you can still do that within a dose response framework.
I hope you found this video interesting. If so, you may want to check out our other videos. If you have any comments or suggestions, please feel free to contact me.